this lecture we will discuss another constraint based approach which is similar in spirit to minimization of metabolic adjustment we saw in the previous lecture, but this tries to minimize the number of flux changes from a given flux vector. The alternative approach that I just talked about, which is closer to in spirit to the L0 norm optimization, is again tries to predict the metabolic steady state following the adaptation to a perturbation. So, the premise is that the organism adapts by minimizing the set of regulatory changes. In the previous case we talked about minimizing the distance from the wild type flux, the whole flux vector as such, organism does not think vectorially, right. So, the wild type vector and the deletion vector are as close as possible in space. Why can't it be the same? Because you have changed a constraint. If that constraint is useless, right, it is possible that you deleted a reaction that was not carrying a flux, then you will sit right there. If not, you will have to move away from it. So, here the premise is the organism adapts by minimizing the set of regulatory changes, which makes somewhat more sense, right. So, the organism only says my budget for reorganization is about 10 enzymes. So, I will try to change 10 fluxes and try to keep as close as possible to the original vector. So, non-significant flux changes are defined using a range and ignored, right. So, you basically say that flux can change by 2-3%, it is not a big deal, but any change more than 5% I want to minimize it. The number of 5%, 10% changes will be minimized. Mathematically this becomes an MILP problem, a mixed integer linear programming problem. What is the formulation? The formulation looks like this. So, in this formulation we are trying to minimize the number of significant flux changes, and you proxied that by another variable yi and you are minimizing that. And if you carefully look at equations 1 and 2, it essentially points in that direction. So, what happens when, so if you basically ignore these, let us just say that delta is 0, epsilon is 0, that would be a very strict kind of condition, right, saying I am not tolerating any flux change, right. So, if you say delta is 0, epsilon is 0, then W and WL are both W, right. So, then your equation basically becomes, what happens to the equation? When yi equals 1, it will be V minus V max, V less than equals V max and V greater than equals V min, right. They basically simplify to the trivial constraint, right. So, even if you do not have even if you have delta epsilon. So, we are saying yi equals 1 for a significant flux change in Vi and yi equals 0 otherwise. For yi equals 1, the inequalities do not impose any new constraint. When we have yi equals 0, it constrains Vi to the ranges defined here. So, within some epsilon, so this is some percentage, delta is some percentage change and epsilon is something above that. So, these are essentially two parameters that you can tune to assess your predictions, right. So, they basically said that delta equals 0.1 and epsilon equals 0.01 was good for lethality predictions, whereas for predicting growth rates these deltas were more reasonable. The main idea here is that you can come up with different formulations based on what makes more sense with respect to the biology you are interested in, right. Is it more important to minimize the overall flux changes, or is it more important to minimize the number of flux changes, and so on. So, to come back to the previous question on where is the steady state, it turns out that MoMA predicts the transient metabolic states following perturbation, whereas Rome predicts the steady state after adaptation, which does seem very reasonable, right. So, the cell initially tries to minimize the overall change, but it settles down to a state where there are only few changes from original. So, everything responds, but finally the cell settles down to a state which is similar to the original state, but has a few more changes, right. So, in many cases, in different cases MoMA and Room have shown better performance and so on. So, Room is also able to predict steady state growth rates and find alternative pathways, but you will see that in current literature most of these techniques are not very heavily used. People still use mostly FBA, but these techniques have some very interesting offshoots, as I will try to tell you in a later class, because we have some recent work wherein we find this MoMA room based formulation is very nice to understand how an organism reroutes its fluxes under a perturbation. So, what is the minimal rerouting an organism needs to achieve and so on. So, this is the pictorial representation. So, this is plain old linear programming, right. We have been talking about this for the last few classes. So, I have some linear constraints and this dotted line is your objective function, it is a linear objective function. It says maximize V1 plus V2, that is this line. In the next, let us look at panel C, where basically you have a quadratic function. What is the function here? The distance which is shown as a circle, right. So, you can think of concentric circles as expanding distance around the original wild type point, and you have moved to a new point based on the deletion. Your new constraint has brought you this, right, and this is a mixed integer linear programming. Why is it integer? You want the solutions to be in, some of the solutions to be integers, maybe x is can be so some of the solutions can be integers, and then you have nonlinear programming. You have a some optimization function like minimize V1 minus 2 the whole cube plus V2. So, this is how the objective function looks, and maybe this is your optimum.
Sir, in the case of quadratic programming, I don't understand. The constraints are linear.
Yeah, the objective function. So, in all cases, the constraints are linear.
And
the objective function for optimization is nonlinear, mixed integer, or whatever. It's the wild type flux, original flux. This was the previous optima, and this is the new.
So, where the circle intersects with the constraints?
Yeah, like what we had here. So, this is the original feasible space,
yeah,
right, which means your optima was likely here, right, or here, right. Now, I have a change, right, which means my FBA predicted optimum will be here, whereas the MoMA predicted optimum will be here, closest to the, you basically drop a perpendicular from there, right. So, closest to the, so this is VW, this is VD, and you get this by minimizing which is nothing but a QP.
And for you said room mathematically becomes a mixed integer.
Yeah.
Why?
Good question.
Okay, why do you say that one of the
Yeah, but V, your answer is V, right? Why should V be all integers?
So, V and Y, you have two sets of, that is why it is mixed integer linear programming problem.
Y is in, no, I don't.
Y is an additional variable.
Yeah, but why should the solution of V be all integers to satisfy?
V is not integers. So, V are reals, that is why it is mixed, otherwise we would have called it an integer programming problem, IP.
Just that your objective function is minimizing integer values.
Yes, and see, you have introduced new decision variables into the mix. You are initially trying to only modify, you are initially trying to find only VI's. Now you are trying to jointly estimate VI's and YI's. YI's are all integers, VI's are of course real numbers. So it intersects all the integer points. So maybe I could even draw it a little differently. I will have to show V1 and Y1. It's too difficult to show it in one dimension, but it has to pass through the grid points.
So all
Right.
range
So in some sense you can just think of it like this. your V, let us say the x axis is Vi, V1 and the y axis is Y1. So, y values have to be integers. So, you will only consider the places where this objective function intersects the horizontal grid lines. So, in this lecture we covered another interesting constraint based modeling technique known as ROOM or regulatory on off minimization, which tried to minimize the number of flux changes. This has implications for other kinds of things as well, which we have not discussed today. For example, how do we find the rerouting that happens in metabolic networks on the deletion of a particular reaction. In the next video we will go back to MATLAB. We will have a lab session wherein we will understand FBA, the various components of the linear programming problem, by using the simple function called linprog, which is the standard LP optimizer in MATLAB. We will also understand what is the Cobra toolbox for MATLAB, which is a very popular toolbox for doing constraint based reconstruction analysis. That is what Cobra stands for. So, what does the model structure look like for a Cobra based model, and how we can perform FBA using the Cobra toolbox.